Hello, this is Lab of Physics 2211, The Falling Slinky by Laura Castano. First, let's start with the objective of this lab. The main purpose of this lab is to predict and analyze the motion of a slinky stretched out falling from rest. I want to answer the question of whether or not the bottom of the model slinky stays stationary just like how it does experimentally. Some key ideas is first Newton's second law. We will use the law to calculate the velocity and the position of the falling slinky. The forces taken into account in our system, which is the slinky and the Earth, are the gravitational force, drag force, or air resistance, and the tension force of the slinky. The gravitational force works in the negative y direction, and the drag force, which is proportional to the square of the velocity, times a proportionality constant. The force of the tension that it has on the bottom of the slinky would be the slinky force. The tension is the same, so that is why the slinky doesn't move until the top of the slinky has reached the bottom. These forces added up makes up the net force. Okay, so now we're using tracker. This is how we calculated and analyzed the motion of the slinky. So the origin is basically on the bottom of the slinky, set in 0, 0. And we track the position of the slinky by measuring the center of mass in each frame, as shown here. As we can see, this is the data points. And we can see that the bottom of the slinky is motionless until the full slinky closes together and starts falling down to the ground. It is the tracking of that, as we can see in this graph. So at the beginning, the graph is right on the x-axis because it is not moving at all. But when it starts moving downwards, when the slinky closes, then it's a sloping, down-sloping graph. And the slinky falls, as we can see, into the ground in a single mass with constant acceleration. So the main changes made in the glow script code were first the initial conditions. The position it's 0 except in the y-axis, which is this value, and the initial velocity is 0, 0, 0. We also added the gravitational constant as well as the proportionality constant, which was calculated experimentally. In the first while loop, it was the time between the start of the track of motion until just before the end of the slinky stopped being motionless, so until the top and the bottom of the slinky met. During this time, the weight force and the force of tension of the slinky were the exact same. And the reason behind this is that this is the reason why the slinky is motionless until the top meets the bottom of the slinky. Also, the momentum principle was coded, the position update, and the velocity update formulas. In the second while loop, the time represents um, when the body of the slinky was in motion. So when both sides of the slinky met and they start falling down. Here, the weight force and the drag force are no longer the same, and that explains why the bottom of the slinky stopped being motionless and why gravity starts bringing down the slinky to the ground. And also the momentum principle was again applied to calculate and update the velocity and the position of the slinky as it falls down to the ground. So when we run the code, this is the final result, and this is the graph. At the beginning, and the x-axis is stationary, just as the tracker code, and then it's a downward sloping graph. So let's compare the results. In the graph of tracker, we can see that until the first second, the bottom of the slinky remained motionless. That's why it stays on the x-axis. Then from that moment on, the slinky filled as a single mass continuously. Below is the graph that the glow script produced, which was somewhat similar. However, we can notice that the falling trajectory isn't straight and the tracker has a lot of deviation. It's straight, sorry. The glow script is straight, but the tracker is not, and we can see a lot of deviation. And this may be because the tracker may not be including all the forces, such as the tension that could be residing in the bottom and the top of the slinky. So as we compare both graphs together, we can see that falling motion is slightly different, but at first both graphs are identical. So from this, we can explain that the sling is motion. Um, Basically, the bottom it's motionless due that the tension and gravitational forces are the same, and that means that they cancel out. However, until the top of the slinky meets the bottom, the two forces changes, so that's why the slinky falls in a single mass. Due that both forces are different.